All right, 818 race car. So we have a car that starts position 0 and it has a speed of 1. And we can give our car two instructions. So the two instructions are accelerate. If we give it an accelerate instruction, it will increase our position by our speed, and then we'll double our speed here. And if we get a reverse, or if we give our car a reverse instruction, then we essentially reduce our speed to 1 and flip the sign. So if our speed is positive, we're going to change the speed to -1. If the speed is negative, then we just change the speed to 1. Okay, and then we just have some target position we're trying to reach, and we want to return the minimum number of instructions to reach that target. All right, so now for the algorithm. So what we're going to do is we're going to breadth first search through all the possible instructions step by step until we hit our target. And once we've hit our target, we can just return the number of steps in our BFS that it took to reach that, and that would be the number of instructions. But what's important is that we limit our range of where we let our car venture out to. So when we give our car an instruction, we're not going to go through any paths of our BFS that take our car outside of this bounds that we want. So the bounds that we're going to set our car to is position 0 to 2 times the target minus 1. So we're not going to let our target go into negative numbers, and we're not going to let our car go past 2 times the target minus 1. And now I'm going to explain why. All right, so let's go over some basic intuition. So let's say this is my starting point here. This is my start, and our speed is 1. Now, let's say that there's some target position out here. All right, so this is my target, and let's say that I want to try going into my negatives first, and then into my and then head towards my target. And so the first thing we're going to do is we're going to reverse. So now our speed is -1, and we're going to accelerate in this direction some amount. We're going to stop, and we're going to reverse again. So now our speed here equals 1. And now let's say that we accelerate all the way to our target, and we just magically land on our target by going this way and then this way. Well, what we could have done instead is we could have started from this exact same point. Okay, so we could have started from the exact same point, and see this amount here. So we had a speed of 1 here, and right now we also have a speed of 1. Let me make that one a little clearer. So we have a speed of 1 here, and we have a speed of 1 here. Well, that means that this amount here, this huge arc, we could have done it right from the beginning. So let's just do that. And this takes us somewhere out here. So whatever, let's just call this distance d. This is also distance d. And this distance, let's just call this, I don't know, d2. Let's just call it d2, all right? Well, after we reverse here, let's put our target right here. After we reverse here, our speed is going to be -1. And this distance d2, notice our speed here was -1. Our speed here is also -1. We can just repeat this acceleration. So we're going to repeat d2's distance. And now we're going to land on the target. So this is d2. And why is this better? Well, notice here we had to do a reversal here, and we had to do a reversal here. Well, here we only had, from here we only had to accelerate, reverse once, and then accelerate again. Versus here we had to reverse, accelerate, reverse, accelerate. So going into the negatives when your speed is 1 isn't better. So I just wanted to prove that we don't have to go into our negatives to wind back and then go, and then shoot forward. All right, so for the next one, let's get on to that. All right, so for this next point, let's say again my start position is here. And let's say I want to try going for my negatives again. So let's just say that I accelerate all the way out here. And let's say that I reverse. And now I undo all that progress and go straight back to my start point. And now, but the only difference here is that my acceleration is going to be a little bit bigger. So now or it could be a lot bigger depending on what this distance is. But the point is, I'm going to accelerate again. So for one more instruction, let's say I can accelerate all the way out here. So what did we just do here? We accelerated, undid 100% of our progress, then accelerated into our negatives. And let's say that my target is somewhere out here. And now let's say that this acceleration takes me, we could say it takes you directly to the target, a little bit before or a little bit after the target, somewhere around the target, right? Well, I think if you just look at this visually, it doesn't make sense. Like, why would we go why would we accelerate in some direction and then undo over 100% of our progress just to get way further away from the target? and then accelerate towards the target, when we could have just done a straight shot. And this won't necessarily take us to the exact same position as, say, where any of these three positions are located. But I think it's easy to see how, like, we would have had to have done all these instructions here, done a reversal instruction, then redid all of those instructions plus one more, and then repeat some more instructions. So we did like one huge loop. And I think just visually you can see that can't be, there's just intuitively it shouldn't be better than just going, say, somewhere over here, and then, you know, continuing to accelerate towards our target, or say going from here to, say, a little bit past our target and then accelerating backwards. So I don't have a solid, like, hard proof for this, but I think visually you could see why just undoing 100% of our progress into our negative positions to do some huge loop, it just doesn't make sense, or just visually it doesn't make sense. But yeah, so I'm just proving why we don't need to go into our negative positions. All right, so on to the next thing. All right, so for this next example, I just want to show that we don't have to check past 2 times our target minus 1. So for example, let's say that my start point, my start point's always at 0, right? And if I accelerate, I'm going to end up at 1 because my speed starts at 1. And if I accelerate again, I'll end up at 3 because 2 times 1 is 2, so 2 plus 1 is 3. If I accelerate again, so if my speed here was 2 in between these 2 points, my next speed will be 4 because I doubled my speed. So that means 3 plus 4 is 7. So I'm going to end up here. All right, so from here to here to here. Now, if I were to double my speed again, so my speed here was 4. If I double my speed again, it'll be 8, right? So 8 plus 7 is 15. So let's say I'll be all the way out here. Now, notice how this relates to our target. So our target is 8. What is 2 times our target? That is 16. So 2t equals 16. 2t minus 1 is 15. So the most we can ever overshoot in a single instruction, the most we can ever overshoot our target, so let's say we overshoot it in one instruction, is at most we will always end up at 2t minus 1 at most. And, you know, we could just keep going, right? So we could just say so it took us, our speed here was 8. So we could increase our speed to 16 and then keep going out here to, like, say 31. But it doesn't make sense to, like, you know, if we're even twice as far from our target, that's not going to decrease the number of instructions to get to the target. Because on top of that, we'd have to do, actually, no, yeah, I think that's good. So, like, just being twice as far from the target. So if we go past 2 times the target, it doesn't make sense. It's not going to decrease the number of instructions. So what I'm trying to prove here is that we don't need to check positions past 2t minus 1. And if, let's say, and it's not possible to reach 2 times t, because if it was, we would have already been at t, because t would, let's say our target was 7, right? If our target was 7, we would have landed on it. So it's not possible to reach 2t, assuming we just bound our, so yeah, we're just trying to bound the positions that we check to 2t minus 1. Okay, so next. All right, so let's code this out. First thing we're gonna do is create a queue of a pair of integers, and I'll explain what this represents in a second. Let me just type this. Okay, so all we're storing is the speed and the position in our queue. So a pair of speed and positions in our queue. And we need a set of visited nodes. So set of pair of integer, and just call this visited, because we don't want to recheck the same positions over and over again, right? Same positions and speeds. Okay, so this will be a new hash set. And we need to put something in our queue. So what's the very first starting point, which is just, the problem said we start at position 0 with the speed of 1, so we just do queue.offer, new pair at position 0, speed of 1. Okay, and then we need to mark this node as visited. So visited.add queue.peak. So that'll just, queue.peak will just grab this thing right here. All right. And yeah, so let's just keep going to BFS. So now while the queue isn't empty, then we can go ahead and pull something out of our queues, or we can pull the node out of our queue. So this will just be pair of integer.integer node equals q.poll. And then I'm just gonna store the things inside the pair into some variable so it's more readable. So in position equals node dot get key, and int speed equals node dot get value. Okay. So we need to return. So the whole point of the problem is to return the minimum number of instructions, right? So we need to keep track of, since we're going through we're going to go through our BFS one level at a time, and the level that we're on essentially represents the number of instructions that we've given our car. So we need to keep track of the level that we are at in our BFS. So the way I like to do it is I keep a size variable. So I'm just going to initialize this to 1 because there's one thing in our queue right now. And we're going to keep track of our number of instructions that we've given the car. And it's 0 in the beginning because we haven't given our car any instructions yet, right? Okay. So what I'm going to do here is if the position equals, so if this position here, if the position out of our node is equal to our target, just return the number of instructions. Oh, return. Okay. So in the beginning, this will just be 0, right? Because we initialize this to 0. And if 0 happens to equal our target, then we'll just return 0 because we haven't given our car any instructions. Okay. And now we're going to go through all of our possibilities, but we only have 2 possibilities, right? Either we accelerate or we reverse. So I'm going to write a little helper method in a second, but what I'm going to do is I'm going to call my helper method offer. And what I'm going to do is I'm going to pass in the queue, pass in visited, pass in our I'm going to pass in our next position. So this is going to be position plus speed. And then we want to double our speed. So you can think of this as the accelerate. So this is going to be speed times 2, or we could do 2 times speed or whatever. And I think that's it. I think we're good there. It might be, if I'm missing something, I'll figure it out later. And then we need to do our reverse, right? So then we'll do offer, queue, visited. Our position will stay the same because all we're doing is we're reversing. We're not actually moving the car anywhere. So position, then we do, if the speed is greater than 0, then we're going to set it to -1. So if the speed is positive, just set it to -1. If the speed is negative, then set it to 1. Okay. And then, okay, so now, again, we need to keep track of what level we are in the BFS because that represents the number of instructions that we are currently at. So, because we're only doing 1 instruction at a time, like per layer, if that makes sense. I'm having trouble wording it, but anyway, we need to decrement our size. So after we decrement our size, if it equals 0, that means we've gone through all the nodes or this set of instructions on this level. So if it hits 0, we need to set our size to the number of nodes in the next level, which would be q.size, and we increment our number of instructions by 1. So just increment the number of instructions. Okay. So, and then there's a couple, I've seen other people, sometimes they do like a nested while loop to go through all the nodes in the current level. You could do it like that way too. I just like to do it like this because I prefer not doing a nested while loop. But anyway, so the last thing we need to do is we need to write this offer method to go through. Yeah, we just have to implement putting this stuff in their queue. So let's do that here. So public or private void offer. So we need to pass in our queue, which is just a queue of pairs of integers, and just call it queue. And then we need to pass in our visited. So a set of pair of integers, and just call it visited. And then next we need to pass in the position. We need to pass in the speed. And int speed. Okay. And now we need to do some checks. So one, we need to check if we've already visited this, right? But we also need to check if this position is outside of our range that we wanted to check. So if it's in the negatives or if it's past 2t minus 1 or 2 times the target minus 1. So let's just check, is position greater or equal to 0? And position is less than or equal to 2 times the target minus 1. Oh, I didn't pass in the target. That's what I forgot. Or we could just do 2 times less than the target. That would be fine too. It's a little bit shorter. Let me just pass that in really quick. So I forgot to pass in this guy right here. Let me just do that really fast. So target and target. Okay. So as long as we're in the correct range, then we can continue to add it to our being BFS through this path. So and then we also need to check that it's not visited. So and visited doesn't contain this pair. So we can just do new pair of position and speed. And it's pretty long. Let me just put this on another line. Okay. I think we're good here. Yeah, so if we're in the right range and it's not visited, then go ahead and add it to our visited. Or you know what? I should just create this new pair in a variable here. Just call this node. Okay. And put spaces because I'm picky about my spacing. Okay, node, new, visited.add, node. Okay. Oh, and if it contains a node. Okay, yeah, so if it's not visited, then go ahead and add it to the visited. And then we can go ahead and do queue.offer the node. And this is just like the neighbor, right? I could have called this neighbor or node, doesn't matter. But anyway, moving on. So yeah, I think this should work. Oh, and I need to, okay, so we're never gonna get to this return statement. Because this return statement here should never be reached because eventually our position will hit our target and then we'll return the number of instructions. So you could put like 1,000, -1, whatever, but we're never going to reach that point. So anyway, just run the code, see what happens. Cool. And just use the example test cases, make sure it's good, submit. Okay, cool. All right, so now let's talk about the time complexity. So our breadth first search, it's just visiting all the possible combinations of positions and speeds because we're holding pairs of positions and speeds, right? And we're just making sure we don't revisit those same positions and speeds. So all we need to do is figure out how many different positions there are, what are all the different speeds we can hit those positions at, and then multiply it together. So we're just doing the number of positions times the number of speeds. So the number of positions, if you remember, is just 0 to 2t minus 1. So this boils down to 2t, and then because we dropped the constant, this is just big O of t. Let me just comment this out. So the number of positions boils down to O of t, and then the number of speeds that we can hit those positions at. Well, what's our first speed? So our first speed is going to be 1, right? And then it's going to double to 2, then it's going to double again to 4, then 8, and this will actually keep doubling to up to t. And I'll explain why it goes to t, but just go with me for now. So assuming that it goes from 1 to t, this ends up, because it's doubling, this just comes out to log of t, or big O of log of t. I think it's log of t plus 1, but when you do the big O, you drop the constant. So it just comes out to log of t for the number of speeds, or big O of log of t. And now why does it only go up from 1 to t? And I kind of went over this earlier, but yeah, let's just go through an example. So let's say the target is 8, right? Well, what's our starting position? Our starting position is going to be 0, sorry, not 1. So starting position is 0, our starting speed is 1. Now, what's our next position going to be? It's going to be 1, and our speed is going to double, right? Then our next position will be 3, speed doubles. Next position will be 7, speed doubles. And so right now we're at position 7 and our target is 8. So now let's add 8 to 7. So this takes us to 15. And this is 2t. This is 2t minus 1 here. And our speed doubles again. Or sorry, that should be 16. Now, this 16 here, so there's only 2 cases where we hit or we ever have a speed of 16, or where we have a pair of, where 16 is the speed in our pair, and that's when we start from the very beginning and go and accelerate all the way to the end, or when we start from the end and accelerate all the way to the beginning. So we don't care about those 2 nodes because it's only 2 nodes, right? Out of if we have like a million nodes, who cares about 2 nodes? But
So we can just like ignore the 16 there. The number of speeds here though is 4. And what is log of the target? Log of the target. So log of 8 would be 3. So the number of speeds ends up coming out. The majority of the nodes can be hit by log of our target plus 1 number of speeds. So hopefully that makes sense. So like, yeah, so log of 8 would come out to 3. And notice that we have 4 digits here, so this just ends up being 3 plus 1 equals the number of speeds on average that the number of nodes can be hit by. So that means that our total time complexity, if our number of speeds equals big O of log of t, our total time complexity equals big O of t times, because the number of positions times the number of speeds, times log of t. And now the space is going to be the exact same thing, because this is the number of nodes that we are visiting, and we're storing all these nodes. This is in the worst case, we're going to run through all these nodes, right? And then we're going to put all those nodes in our visited set. So our visited set is what's growing our space. So then the space just ends up being the exact same thing. It ends up being O of t times log of t. Okay. Yeah, if you like the video, you can give it a thumbs up. You can subscribe. Cool. Bye.